This is 1-1, I would call it section B for college algebra. So the skills required here are algebraic tests to check for symmetry, understanding symmetry, x-axis symmetry, y-axis symmetry, origin symmetry, or thus no symmetry, and then symmetry with identifying intercepts, which we talked about the x and y intercepts in part A. All right, graphs of equations can have symmetry with respect to one of the coordinate axes or with respect to the origin. X-axis symmetry. This is symmetry with respect to the x-axis, means that when you fold the Cartesian plane along the x-axis, the portion of the graph above the x-axis coincides with the portion below the x-axis. The graph of an equation is symmetrical with respect to x-axis when replacing y with negative y yields an equivalent equation. So thus the points x comma y and x comma negative y are both on the graph. So just for a quick in general sketch, this is what looks like. So if you folded at the x-axis, you would see they would look the same. So if I pick a point right here, this point is x comma y. If I do the equivalent point down there, you're going to see it be x comma negative y. That's when you know it is a true reflection. And that would happen everywhere on this graph if it's reflecting, or if it's symmetric, not reflecting, symmetrical across the x-axis. Y-axis symmetry is symmetry with respect to the y-axis, means that when you fold the Cartesian plane along the y-axis, the portion of the graph to the right of the y-axis coincides with the portion below. Really, it's just to the left, so we'll cross that out, to the left of the y-axis. The graph of an equation is symmetrical with respect to y-axis when replacing x with negative x yields an equivalent equation, and we're going to talk about what that looks like. And then xy and negative xy are both on the graph. So we'll do a sketch of what that looks like. All right, so parabolas, especially your traditional parabolas that we end up graphing, the y equals x squared, is a great example of this, because here, like this point, x comma y, and then the corresponding point over here is negative x comma y. So the y values are the same. Same thing down here, right? It would still be whatever the x1 comma y1, and then over here would be the same thing as negative x1 comma y1. So I just picked another point there. Equivalency is going to be, it's if you folded it at the y-axis, you would see the same thing. Origin symmetry, this one may be a little more trippy in the brain, is a graph is symmetric with respect to the origin if whenever xy is on the graph, negative x negative y is also on the graph. The graph and equation is symmetric with respect to the origin when replacing x with negative x and y with negative y yields an equivalent equation. And like I said, we're going to do the algebra for that. So a sketch that follows this is like this one. So this point right here is at x comma y. The corresponding point over here would be negative x, negative y. So that's, if it's around the origin, is you're going to see that pattern going, and it's always going to be, the values would be the same, but they're going to be the negative numbers of those. So like I said, this one may be just a little bit different to get. All right, so then, but they ask us to test for symmetry. So we've got to test for all possible symmetries. And so we're going to do that algebraically. So we're going to start with the x-axis. And how we're going to show this is, we know we're talking about y equals 2x cubed. And on the x-axis for symmetry, it talked about your negative y would show an equivalent equation. So if I would then solve for this, right, this becomes y equals negative 2x cubed. Well, negative 2x cubed is not the same as positive 2x cubed, so this is not an x-axis symmetry. So again, since this equation and this equation are not equal, it is not x-axis symmetry. So now we're going to take the same equation and try it for y-axis. So what I do for the y-axis is now I'm doing that with the x value. So where I see an x, I'm now in parentheses going to put a negative x, and I'm going to see what happens in this math problem. So when I simplify this, I end up with a negative 2x cubed, because negative x raised to the third power is a negative x cubed. And so just multiply that by 2 and you get a negative 2x cubed. So now, again, I have this and I have this. These are not the same, so it is not y-axis symmetry. And they have to be exactly the same. Now, you might be thinking, are we just going to have to keep doing this until we prove that there is none? Sometimes, yes, you have to test all three main ones to then prove that there is not symmetry. But let's go into the origin one. All right, so the origin one is different. So now we are replacing the y with a negative y, and we're replacing the x with a negative x to test if this is symmetry. So when I work through this problem, I still get a negative y is equal to the negative 2x cubed, as we saw in the last one. But I need to solve for y to get y all by itself. And when I do that, I get a positive 2x cubed, because I would divide both sides by the negative. Well, these are the same. So this would be a yes. This is origin symmetric. Because the equations are exactly the same. So here we are testing for origin. I'll go ahead and give you a highlight that. That was origin symmetry for this one.